session chair for this session, which I call a present and ex-Singaporean session, because all the speakers here are linked to Singapore in some way, either presently or in the past. Reynold has visited our NUS at least for 1 week, so I consider that a friend card. So Reynold graduated from Purdue University, and that's why there's a distinctive figure of the two people here today. That's why I assume. He had been in Hong Kong since 2001 or 2008. 2008, sorry. I was visiting him in Hong Kong for 2008. He was the recipient of 2012 Research Profit Prize in the Department of Computer Science and Engineering. He was the vice chairperson of ACN for 2013. As all of us is member of IEEE ACN and Special Income Group in Singapore. He received an outstanding service award in CIM. Let's go Reynold. I think all we should do.
Yes. Thank you, Anthony, for a very excellent introduction. And now it's my turn to give my presentation. And I really appreciate for all your effort, and especially I think all the speakers before me are doing very well. This gives me a lot of pressure. Anyway, okay, so today I'm going to talk about how to do search and analysis on heterogeneous information network. Okay? So following Kevin's excellent presentations about how to do analytics of structured data. Okay? So let us try to see if we can follow up on these discussions. Okay? So as Anthony has introduced, I actually am a graduate from Hong Kong U, so this place I have a lot of feelings and emotions about that. Then I did my study in Purdue, and then at that time I met Professor Ahmed and Professor Mohammed, and we become very good friends. I'm really very pleased to have them here. And then I have a brief stay in College before joining Purdue. Okay? And in fact, my research has been mostly focused on uncertain data management, which I think in the morning Professor Joshi has talked about probabilistic data stream, and I've spent a lot of time dealing with probability in database management. But in this talk, I'm not going to talk about probability. Okay? All right. So, so instead, I'm talking about the so-called knowledge graph, okay, which I think is one of the major data sets, okay, that's available, okay, and still a very active research area. Okay. So knowledge graph, okay, or graph itself, it is a very large data source in which different nodes, okay, or different entities, okay, they are connected, okay, in a very complex manner. Okay. So you have, for example, Facebook is a network graph because Facebook is talking about how users are connected to each other. Okay? We have in bioinformatics, the different nodes represent different proteins and how they interact with each other with probability, for example. Okay? And in fact, in many different industry applications, okay, it is common to have a graph connecting different users and their purchase patterns of items. Okay? So you have a large network connecting different users and items in order to provide different kinds of recommendation. And later on in this talk, I will also talk about how we apply our analytics to our elderly care applications. Okay. So generally speaking, this whole bunch of things, okay, all these kinds of graph, okay, basically you can call it a class of graph called heterogeneous information network. So why is it heterogeneous? It is because these nodes, okay, such as, okay, for example, okay, these games, okay, they are not just a node, okay, they're not just the relationship, but you also have a lot of information. For example, you have the labels on the nodes and the edges in order to indicate the semantics and explain how they are related in different ways. Okay. So just to give you more solid examples, suppose, okay, I think I often look at IMDb to look for good movies. Okay? In fact, the IMDb is a natural graph because in the sense that, okay, the IMDb contains different movies, different actors, okay, how are they related to each other, how are the movies directed by which directors. So you can represent, for example, the movies, okay, or the actors and the directors as nodes. Okay? and different colors of the edges represent why they are related. Okay, so for example, the blue edge represented, okay, because they are all popular movies, or because this black edge represented these are the actors related with the movies. Okay. As another example, okay, in Facebook, okay, Facebook, you know, there is a large social network, okay, because you could have different users, and also they probably also maintain some items. Maintains different items in the graph as well, because sometimes you also receive advertisements about the Nike shoes that are worn by viral, for example. So, recommend the same shoes to me, for example. Okay? So basically, this is a large network which is composed of different users, friends, okay, indicating the friendships, and at the same time, what kinds of items they are interested in. Okay? And needless to say, there are a lot of applications on this very rich source of data, because if you are able to extract important information from this data, then you could have a lot of applications that are very useful. So one typical application is, I think it's quite familiar to many of us, is the link prediction problem. Right? So the link prediction problem basically says that, oh, if you have, give me a pair of notes, could it be possible for me to predict whether there will be a link to the future? So for example, in Facebook network, could you predict that there is friendship? Okay? So if that is the case, then this may represent a good opportunity for recommendation. Okay? And HIN, or Heterogeneous Information Network, is also used in, for example, so-called entity profiling. Basically, use the neighborhood information of the graph in order to enrich the information and profile of a node. Okay? And some researchers, like Philip Yu, for example, they also study how to link up different heterogeneous information network in order to do data integration among different graphs. Okay. And our group, okay, the past 2 years, we have also studied how to use HIN to do query recommendation. So by query recommendation, okay, we say that, so if you are typing some keywords in the box provided, okay, then some new queries will come up in order to give the users some suggestions or recommendations for the query. So we are also trying to tap into the very large HIN source, okay, which I will talk about later. One of them is Yahoo. Okay? The other one is G-Base. Okay? So this data source could help us to do some recommendations based on the rich information they have. Okay. So the question that I want to discuss with you today is a very fundamental, and also this issue looks to be quite well studied. Okay? It is about how to find similarity or closeness between two nodes. In the literature, we call this relevance. Okay? So what is relevance? So this is typical HIN, okay, which you can see that different nodes, okay, have different information. So for example, Barack Obama, okay, is a writer and a US president, and he is also a leader, and when you go up to a high level, okay, it is just a person. Okay? So these different labels describing Barack Obama is organized in a hierarchy. And also, okay, in this typical HIN, Barack Obama is linked to other entities or nodes. For example, Barack Obama has a child, Henry Obama, so that is why there is a link with label called has child. Okay? So that is why I say HIN is a very rich source. Okay? It has different labels in nodes and edges. Okay? So Barack Obama is a citizen of the US, okay? And then the question, okay, that often comes in any of the data mining or machine learning algorithms, okay, in the end, okay, boils to the question about how to compare the similarity or closeness between the nodes. So for example, how close, okay, is Barack Obama to George Bush? We know that they are somewhat close, okay, but can we kind of like compute the scores, okay, compute the values between how close they are in order to do better analysis and ranking? Okay. Now, in order to do this, okay, there are already many different measures, okay, proposed in computer science and data mining with different similarity scores. But most of these functions, okay, before the era of HIN, they focus on the graph structure. But how do you make use of the labels of the nodes and the edges in order to do similarity or relevance computation is still a difficult research issue. Okay. So to tackle this problem, okay, some researchers, okay, back in 2011 has proposed a concept called metapath. So what is a metapath? is a very simple concept to understand. Basically, it's focusing on just some high-level relationship between two nodes. So, for example, okay, just look at this very small HIN. Okay, one of the meta paths that could link up Barack Obama and his wife is to say that the U.S. President and First Lady has a child. Okay, so if we read this, okay, the U.S. President, person, First Lady, we don't know who specifically is. Okay, but somehow they are related by this relationship with the label has child on the edge. Okay, so this is a meta path. Okay, but if you go from Barack Obama, Michelle Obama, then there is a very specific path. The meta path is about some high-level information. So there can be many, many meta paths. So for example, just to name a few, they say that the president and the first lady, they're citizens of a country. Okay? So it's through this path, for example, you can also find an instance of the meta path that links this president and first lady together. Okay? And the researchers have basically used these bunches of meta paths to define relevance or closeness between two nodes. So to just illustrate a very simple metric, okay, one metric is called path count. Okay? Path count means we want to count how many times a given meta path is satisfied. Okay? So for example, because Barack Obama and Michelle Obama has 2 daughters, okay? So if we count how many times this given meta path are satisfied, because they have 2 children, so this is satisfied by 2 times, and as a result, we say that the path count or PC between these 2 nodes is 2. Okay? So very simple. But this is too simple, and the researchers like to have more complex things. Okay? So they give the reason why this doesn't work. Okay? So the reason is because this path count always biased towards some nodes that are very popular. Like for example, Barack Obama, okay, they are very densely populated, and as a result, they tend to have a high path count. So that's why, okay, we need to have something more normalized. Okay? So this comes into the second measure, which is proposed also to use meta path. Okay? But this uses a technique called random walk. So have you heard about random walk before? I believe many of you have heard about page rank or seed rank. Right? It basically is a randomized method based on walking on the nodes with some probability added to it in order to find the similarity. Okay? So what this meta path constraint random walk is essentially an extension of random walk measures based on meta path. So what this is saying is that if you give me a meta path, like for example, a person is linked to each tree because they have a child. Okay? So I want to know, based on this meta path, what is the probability that Barack Obama can reach Michelle Obama? Okay? And without showing all the math here, I just tell you that they have a probability for Barack Obama to reach Michelle Obama with a probability 0.5, okay? Because he can walk back to himself, he has a chance to, 0.5 chance to walk to Michelle Obama based on this meta path. Okay? So, in fact, after the proposal of the meta path and the relevance measures, okay, a lot of developments, and we have also done something on this. Okay? But one thing that we find, okay, which is a problem with all these approaches, is that we don't know how the meta paths come out. Okay? So in most of these papers, they say that okay, some experts will give you the meta path for which you can evaluate your measure on it. Okay? But this is kind of a weak statement in our opinion, because very often, okay, there are not many experts in this world, right? And the experts themselves are usually the authors of the paper. Okay? So they assume themselves they know a lot about this graph, okay, which we challenge about this assumption. So that is why, okay, in our previous work, okay, in 2015, we tried to tackle this problem. The problem is not about proposing a new relevance measure based on meta path, but rather finding the problem is trying to solve the problem of how to identify the best meta path to be used. Okay? So the problem is how to find the best meta path, which is turned out to be a very difficult problem. We are still trying to study it. Okay? The reason is because in a heterogeneous information network, it is typically very dense. Okay? So there are many different meta paths between the 2 nodes. Okay? So it is not easy to determine what are the best meta paths to be used. Okay? So to solve this problem, okay, one of our proposals, which may not be the best one, okay, is to use kind of like a query by example approach. Right? So what does this mean? So to understand this, what we are saying is that the user first gives us some examples about how nodes are related. Okay, so the user gives us some input to teach us how two nodes are related. So for example, the user can tell us that Barack and Michelle Obama are related, and Bill Clinton and Hillary Clinton are related. Okay? But the user is not supposed to give us meta path, because the meta path is about the underlying information about the graph, which can be very difficult to specify. Okay? So the user just gives us some example, and with a HIN, like for example, an open graph like Yago, then our job is to try to learn from these example pairs about what are the meta paths that can describe these different examples in a correct and unique manner. Okay, so for example, now given these two examples, intuitively, what you think in your mind, maybe because these two pairs are related because the president and the first lady, they both have child. Okay, so if you know that, both of them have child, okay? And also, they belong to the same political party. Okay? Now, these two meta paths has the property that they have to be, first of all, correctly linking up these nodes represented by these labels, okay, by these persons. And at the same time, these meta paths should be unique. Okay? So you don't have some meta paths which are very common, okay? But they should be only unique to these two persons. Okay? So with this framework, okay, what we are trying to do is that if you give me some examples in terms of node pairs, I will return some meta paths that you think are useful for describing the unique relationships among these example pairs. Okay? So I'll skip the detail, but instead, okay, I will talk about basically, okay, this is a toy example on HIN, okay? And these are the HIN containing different nodes, okay, representing the president, the wife, and the children, okay? So what we do basically is we have to first use the positive examples and the negative examples as our starting node, and then we use some heuristics to try to search, to expand our search in this graph in order to define some priority scores based on the heuristics using machine learning techniques, and in the end, okay, we hope that we could arrive at the meta path saying that pertaining to these positive examples, the meta path could be because, okay, they have a common child. So you see that, okay, starting from this node, they have they go through this has child link, okay, to another node which is a kid, and going back to their spouse. Okay. So basically what we're doing is we have this kind of machine learning approach. We start with example pairs, and then we try to compute what is the most related meta path, and then through this model training based on the least angle regression model, and we can kind of like guess what is the good meta path, and then use this meta path to fit into the model again and see if it converges in the end. And so I will skip the details. Okay. And instead, let me just give you one of our key results. Okay. So in this experiment, okay, what we are doing is we are using Yago, which is an open data source for HIN. Okay. So the Yago data set, okay, has a lot of links. Okay. One of the common edges is so-called citizen of. Okay. So citizen of, okay, is an edge telling whether a person is a citizen of a country. Okay. So in this experiment design, what we do is we randomly pick out some example node pairs and then remove the citizen of edge, and then see whether we can predict the existence of these edges. Okay. So by using our approach, using the meta path in the similarity search, we find that we can extract certain meta paths that are quite interesting, that we think are related to the prediction quality. Okay. So for example, some meta paths are very simple, and experts can also tell us that these are the important meta paths, saying that, for example, the person is born in a city which is located in a country. Okay? But there are some other weird meta paths which our algorithm tell you that they actually carry a lot of weight, a lot of importance. But this may be difficult to be found by a human. So for example, this say that a person is predicted to be a citizen of a country if he is born in a city in which some event happens between the city and the country. Okay? So what our approach can do, okay, is trying to extract some meta path, okay, which can have variable length. Okay? And this meta path are identified to be important. And in this graph, we also show the results of the existing works, in which the limitation is that they have to fix the length of the meta path in order to do the prediction. Okay? But as we can see from this example, in fact, okay, the meta path have variable length, okay, and some of them are difficult to detect with human intuition. Okay. So the second part of this talk is about how can we further leverage the meta path. Now we know meta path again is just to tell you that how the nodes are linked to another node with a path relationship. Okay? But sometimes you may actually want to have some more expressive and rich expression of how two nodes are related. Okay? So for example, I want to say that hey, two nodes like A, it means authors. Two author nodes, okay, in a bibliographical network, they are related. If the papers, okay, something paper P1 and P2, they're just papers, okay, they are published in the same venue and mention the same topic. Okay. Now, notice that now authors A1 and A2, they are not linked by one single path anymore. But instead, you can see that there is a nonlinear relationship in which okay, these papers are not just related because they are published in the same venue, but also they mention the same topic. Okay. So we call this concept the meta structure, okay, which basically is a generalization of meta path to express a more complex relationship between them. And we have used the meta structure to try to generalize the relevance measures based on meta path. So for example, we can say that how can we quantify the relevance between two nodes is based on how many times the occurrence of the meta structure instances given a meta structure. So we call it a structure count. Okay? And if you still remember, okay, we just talked about this path constraint random walk based on meta path. And we can also define a similar measure based on meta structure. Okay? So basically, it is a random walk based on meta structure. Okay? And we can still define the probability of similarity between two nodes, but this time it is walking on a meta structure rather than walking on a meta path. And this itself is a very interesting problem because this also involves how do you define the meta structure. And we find that the meta structure has to be defined in terms of a directly cyclic graph, a DHA. Otherwise, okay, we will not be able to do a sum random walk. Okay, so I will skip the detail here. Okay, so anyway, it requires a certain expansion of state in order to define the similarity among different nodes. Okay, and we have used a cache table to speed up the process. We'll skip this. Okay, so to summarize, okay, what we want to talk about here is that based on first of all, okay, for heterogeneous information network, okay, meta path is a good tool to define relevance. Okay, and there are different ways to do this. Okay, and in our work, we try to study first of all how to find meta path, and secondly how to extend meta path to meta structures. Okay. And we have also done some experiments to verify the effectiveness of our approach of using meta structures. Okay. So one of the applications that we are interested in is to remove duplicates from a heterogeneous information network. Because you know, Yago is an HIN, but it actually comes from different sources automatically and manually. But it is inevitable that sometimes the entities or nodes are duplicates of each other. Okay? And this may somehow hinder analysis. So for example, we find that in Yago, okay, there is a node called Barack Obama, and the other one is called President of Barack Obama. Okay? They're considered as two different nodes, but there's a very high likeliness that they actually belong to the same person. Okay? So how can we detect these duplicates? So one way to do this is to use meta path or meta structure. So for example, we can say that two persons are married to the same person, then P1 and P2 are actually the same person. Okay? Or another meta path is to say that if the two persons, P1 and P2, they are affiliated to the same organizations, then they are the same person. But this may also be some very weak constraint. So maybe it's better to say that P1 and P2 are only the same person if they are married to another person and belong to the same organization. Okay? So this imposes a stronger constraint in the analysis, and we find that with the area under the curve measure, okay, our approach can give the highest effectiveness. Okay. So in fact, okay, we have a very short demo to demonstrate how we use the meta path in this query by examples on structured data. And actually, this echoes to Kevin's talk about how can we manage and structure data better if easier to use query interface. Okay? And it's worth mentioning that, okay, in fact, there are many graph query languages for structured data as well. Okay? So database, you know, there are used for relational tables with SQL query, okay? And for graph query, graph database, you also need to learn new languages, okay, in order to access them. Okay? But what we want to do is we want to use this concept of meta path to see if we can allow the search easier. So let me explain this. Right. So we call this a query by example search, which is based on the meta path technology. So for example, okay, the users can enter the keyword Obama, and then based on Obama, they can find out who are related to him. Okay? And let me skip this. Okay? And what we want to do is that we want to use this interface to kind of like find out, okay, whether we can learn new pairs of couples who are also US presidents and wives. Okay? So the user with this interface, they can drag the president's name, okay, to the source node. Okay? Okay? For example, they can drag Bill Clinton and Barack Obama. Okay? And they can also put the first ladies, okay, if we have some information about these first ladies, of course, and the Bill Clinton, Barack Obama, and their wives, etc. Okay? And based on this source and target nodes, then, okay, we can press the run button, and we can learn all the meta path which connect all these three pairs. And furthermore, we can use this meta path to learn new node pairs that the user may not know. Okay, they can only know that the US presidents and first ladies are related for three pairs, but with the meta path, we can give them more answers. Okay, to tell them that actually Jimmy Carter and Rosalind Carter, they're also having the similar relationships in terms of meta path. Okay? Because of the limitation of time, I also just want to use this opportunity to introduce our recent project, which I think is very interesting application of HIN and meta path. So recently we have got an ITF project, okay, which is a collaboration with our social work experts in our university, and also the ASTRI, which is a pioneer institution in Science Park, okay, for making technology work for society. So what we are interested is we find that in Hong Kong, like many cities, okay, the aging problem is very serious, and we know that in about 20 years' time, okay, there will be 1/3 of people over 65 years old, and they are still very happy. Okay? So this is a big problem, and also many elders, they have the thinking of not, they don't want to go to the elderly care centers. They want to stay at their home. But at the same time, because of the health problem and because of the deterioration of activities and so on, in fact, they need a lot of help. Okay? They need a lot of helpers to give them transportation to clinic or just buy lunch boxes for them and so on. Okay? So that is why, okay, Hong Kong SKH, okay, Sengkong okay, SKH is our collaborator in this project, in which they are one of the largest NGO for providing services in Hong Kong. And with one of our collaborators, Professor Terry Lam, this guy, okay, he is actually one of the pioneers in novel projects for elders. So one of the projects they have is called Time Bank. Okay, so the concept of Time Bank, I don't know if you have heard about it. Basically, the idea is that they want to encourage elders, okay, or even young people to help the elders, okay, by allowing them to specify, okay, how many hours of work they have contributed. Okay? So for example, if I have come to Ryan's home, okay, and help him to do cleaning, okay, then I will save 2 hours in my bank account. So I don't ask him for money. I just save the amount of time. Okay? And later on, okay, because I may need help from CM, okay, I will say that, okay, I want to spend 2 hours of work, okay, can you help me to buy lunch box for me, for example. Okay? So basically, everyone has an account of time, okay? And you can save it, okay? And the more, you can also have debt, okay? Because maybe the organization needs a lot of help for helpers to do voluntary service. So the center may need a lot of help, okay? And it has a lot of debt in terms of time.
Can you give some of your time credit to others?
I think that's possible. Yeah, in fact, they are already doing it in Hong Kong, okay, which from time to time, every year, okay, they have this large booth in which the elders can make some art themselves, maybe some drawings or some handcrafts, okay, and then sell it in terms of time. Right. So that's a very interesting idea. Okay. But the problem is that because in Hong Kong, in fact, we find that there are a lot of NGOs, okay, or charity organizations in which they are not very IT advanced, and they still use pen and paper to do it. So which is very time consuming, of course. So that is why, okay, we have proposed a project which luckily we got funded, and now we have started doing this. Okay, so we call it HINK. So the main idea is that, okay, first of all, thanks to Astrid people, they have already built a good mobile app, okay, in which they are very usable. Okay, they have designers who design nice interface for elders to use. Okay, so what we want to do is we want to build an HIN which connect the elders and the helpless, okay, in a way so that in the back end we have a big knowledge graph in which we can use the knowledge graph to build AI applications to do recommendations. What kind of recommendations? So for example, if I want someone to help me, okay, to clean my house, okay, I may ask Ryan, okay, because now he's available, and I will not ask Byron, even though he's good at cleaning, but he's not available, he's taking care of his kids. Okay? So the HIN, okay, would serve as a knowledge graph in which the applications can be built on that. Okay? And we envision that the HIN itself will be a very valuable data source for different applications. Okay? So that's the end of my talk. I over a little bit, but thank you for your attention.
Very impressive presentation, and congratulations. The record is amazing. It's, the publications are tremendous. One way to extend this work, if you can think of the data scientists, the people that are doing the analysis, they spend something like 80% of their time finding information. Right? So there are thousands and thousands of databases, and they spend a lot of their time discovering the information. And this is what we call data discovery in the wild. Similar to exactly like what you're doing, but take it to the scale of a data lake.
Yes.
And then trying to discover, to find data in the data lake. It would be great if you can see if you can apply some of the techniques that you already developed in that sense, because trying to figure out whether the nodes that you have will be now databases, or they may be tables, or they may be columns. Right? So you've got to draw all of these relationships that you drew, but at a different scale. You're talking about thousands of databases, maybe hundreds of databases, maybe thousands of tables, and so on and so forth. So you may want to explore, doing this in a less clean way, because you assume here you have the ontology and so on, and it's easy to draw these relationships. But think beyond that. Go into situations where the relationships are not clear, and you may assume these relationships, but later on you find out that they're not correct, and so on and so forth.
Yeah, I think it's a very good suggestion. In fact, we are already doing this in this project, because honestly, we don't have any HIN for elders. They just give us some forms or some input from the app. Okay? And on the other hand, they also have something called assessment data, okay, which are done by the social work experts. So they have to fill up some very long forms for the elders. So our goal is to try to use these raw data, which are not in the form of HIN, to put them into HIN. So getting this HIN itself is also a very tremendous process by itself. And so this is one way to solve this data lake problem, by linking different kinds of data, whether the tables, whether the forms or the graph, and everything becomes just entity and relationship, which will make things much easier. Yeah.
You mentioned about what are the semantic relationships and those which has the highest top 5 or maybe different types of relationship have best related about a new set of knowledge and also help to predict something new automatically instead of using yourself, but the machine to learn new relationships, generate new relationships, and then predict something.
Yes, I think this is a very good question. So basically, the main question is if you have new information that comes in, okay, which may give you new information about the graph, for example, new entities or new relations. Or we can become friends today, but we were not friends yesterday. So this essentially boils down to the question of how can you update the results of your machine learning, right? So,
No, actually you have two semantic relationships that you predict would be something important for predicting. But can they be integrated into some new relationships that you don't even know but can be used?
yes.
So that project that we talk about, Avatar, is actually self-learning, that kind of semantic relationships, and the machine itself will generate new entities.
Yes, in fact, that is also one of the advantage of using HIMs because it allows the so-called inference. So what you talk about is inference. Based on the different kind of relationships, you can use inference, and one of the languages is called OWM, which allows you to do inference for new relationships, which can be learned from HIM, which we don't see as before, but because you see they are related in different ways, so you can derive new relationships
So
based
that's
on
not
that.
difficult. That's,
Yeah, that is there. There is a whole logic to talk about how to use edge to derive new relationships. One more quick question.
Yeah, I got a quick question. Can you know how does the HIM or the method path handle outliers? Because in my understanding, for example, there was two professors called Herbinson in NTU. So in this such cases, how does the HIM or method path handle such outliers?
Yeah, I think, in fact, there are many graph algorithms for doing this. There are outline detection algorithms for dealing with finding out the nodes, okay, that may be wrong or they have some information that is very strange, etc. Okay? And also there are a lot of work doing embedding for computer graph into vectors in order to run algorithms on them to detect outlines. So we can talk about this offline.
Just
All right.
a really quick comment.
Yeah.
These Victor at DBT gave talk on learning relations
Yes.
and all sorts of machine learning methods on this kind. I mean, it's similar work, but you know, they don't have like a page rank style. So it would be interesting potentially to look into that.
Yes.
They really focus on inferring this kind of relations.
Thank you very much.
That's our thank you.